Consider the innocent-seeming idea that even if none of us were there to see it, the world would still exist. Most of us don't believe that when we close our eyes, everything around us dematerializes, only to come back into existence instantaneously when we open them. Assumptions like this are very ingrained in our minds, and yet in quantum theory, many of our basic assumptions are false or seriously up for debate. So what is quantum mechanics? It's an attempt to explain a lot of strange phenomena that are often most noticeable when we look at particles smaller than atoms. But make no mistake, quantum mechanics isn't just the physics of small things. It's a complete overhaul of Newtonian mechanics, the explanation for why chemistry even happens, and just in general a huge rethink of how the world works. Our adventure into quantum mechanics starts off with the question, what is stuff? How does it act? We're all pretty familiar with how things act in our daily lives, so this question seems a bit trivial. But people discovered there was another side to stuff that becomes more obvious when you look at very small objects. They started to say strange things like, stuff acts like particles, but also like waves. We'll see how quantum mechanics solves that confusion by telling us stuff is even weirder than that. Firstly, what is a wave and what is a particle, and what are the telltale signs that you're dealing with one or the other? Particles are pretty familiar to us. One thing about them is that they're localized to one area, whereas waves are very spread out and in more than one place at once. There's another way that waves are very different from particles, and that's how they interact with each other. Particles do this, whereas waves can do crazy things like this. This phenomena is called superposition or interference. Basically, when two waves meet, they can either reinforce each other, or cancel each other out, or do a bit of both. You can use these two properties of waves to design a pretty clever experiment that tests whether you're dealing with waves or particles. It's called the double slit experiment, and seriously, you're going to want to remember this one because, in my opinion, it's the most important experiment in quantum mechanics and we'll come back to it so many times. First, we'll talk about the experiment when it's done with small particles. You need a gun that will shoot the particles here. Then put up a board that will detect where the particles land. In between, you set up another board, but one with two slits in it that the particles can get through. What happens when you shoot the particles? Most won't get through, but those that do will mostly end up in two big clusters behind the holes. The situation with waves is very different. We'll have the same setup now, except we'll create the waves at this end, and at the other end we'll measure where the waves hit with the most intensity. First, we'll cover up one hole and see what happens. The wave goes through the hole and then starts to make these semicircular wave fronts. Therefore, the wave hits most intensely right behind the open slit. So you might expect that when both holes are open, that the pattern will look something like this. But it doesn't at all. When both slits are open, the wave splits up and then interferes with itself. When two peaks or two troughs meet, they make a bigger peak or trough. Where a trough and a peak meet, they cancel each other out. Imagine that these are water waves and you're in the water. If you're in these waters, you're getting bobbed up and down a lot. On the other hand, these waters are pretty calm. So at the wall, you can expect the waves to hit most intensely around these areas and least in these. So you'll get a pattern like this for intensity. Most things that we're familiar with seem to act like particles, so people expected that even when we're dealing with things so small that we couldn't see them with our eyes, they'd be particle-like. Let's put that to the test using the double slit experiment on something extremely small, say an electron. We won't be able to see the electron as it goes through, but what we'll do is put a special screen in on this side that lights up whenever the electron hits it. We're going to use an electron gun that only fires one electron through at a time. Here goes. Well, that looks like particles to me, because a wave would be spread out across the whole screen, not arriving in these localized dots. But wait, look at the pattern forming on the screen. That's not what we'd expect of particles at all. In fact, I'll show you that this result seems impossible. First, let's see what happens when we cover up one slit. We get one big splodge of points behind the open slit. Okay,
But what we just found was that the electrons are like particles in that they're in one spot and not spread out. So each electron must go through just one slit. But we already know that electrons going through this one slit must make a pattern like this, and similarly for electrons going through the other slit. So we should expect this, which is not what we're getting at all. This result seems to defy logic, and that is a big problem for physicists. You see, if the universe is inconsistent with itself, there would be no point in trying to make sense of it. It wouldn't work, and physicists would be out of the job. Luckily for us, a few smart people came up with a cunning solution. The solution is called quantum mechanics, and if it's troubling, then please just remember, we were desperate. You see, our previous reasoning implicitly assumed many things that we usually hold to be true, but if we can let a couple of these go, then we can come up with a solution. Our first assumption was that because the electron looks like a particle when it's observed, that means it's a particle while we're not observing it. This is the kind of assumption that is really important in science. We like to think that our experiments are simply unveiling the reality that was already there, rather than changing it completely. Quantum mechanics lets that comforting idea go. Instead, while we're not looking, quantum mechanics doesn't say anything about the actual electron itself. Instead, it talks about something called the electron's wave function. The wave function is this wave that exists at all times, even when the existence of the electron itself becomes questionable. It's a wave similar to a water wave. Therefore, in the double-slit situation, it interferes with itself, so the intensity profile of the wave looks like this, just like with water waves. Okay, great, we've got this wave, but what on earth has it got to do with our electron? This is where we need to let go of our second assumption. Basically, ever since Newton, physicists have believed that there isn't random chance in how our universe acts. If you think back to our experiments with regular particles, we said that they didn't all land in the same spot. However, according to Newton's laws, this is just because they must be going in slightly different directions and speeds at the start. If we could get them all exactly the same, they'd fall in exactly the same spot. In quantum mechanics, though, the opposite is true. Even if it were possible to get the electron gun to shoot in the exact same way each time, the electrons wouldn't all land in the same spot. There is an element of chance involved, and there is absolutely no way to predict where a particular electron is going to go. That's like saying, when I let an apple go, 2/3 of the time it'll fall down, and 1/3 of the time it'll fall up, for no reason, and there's no possible way to predict which way the apple will fall next time you drop it. However, quantum mechanics doesn't say that where our electron will turn up is completely random, because then our pattern would look like this. On the other hand, what we get for the double-slit experiment is this, and for the single-slit one, this. We can see the electrons seem more likely to turn up in some spots, but how do we figure out where? Re-enter the wave function. Remember, the intensity profiles for the wave function in each case is like this and this. As you can probably guess now, the electrons are most likely to turn up where the intensity of the wave function is big. If you want more details on how to exactly calculate this, then let me know in the comments and I might make a video about it. Okay, so let me recap. When we're not looking, the electron itself may or may not exist, but in its place is some sort of wave. Quantum mechanics says that while you're not experimenting on it, the electron doesn't have a position. Even its wave function is spread out. But when we attempt to measure the position of the electron, the universe realizes it needs to produce an electron, so it picks where the electron will turn up, semi-randomly, based on its wave function. Yeah, I know. Well, I'll leave you with that for now, and next week I'll try and expose you to more of this quantum mechanics thing, but I'm sorry, it really only gets weirder. I hope you have a bunch of questions, please ask them all, and I'll answer them if I think I know the answer. See you next time.